Hello, everybody, and welcome back to another wonderful interview here with one of our longtime charity partners, Fred Hutch, and with our friend here, Guppy. It's now, as most of you who are maybe watching this know, this particular marathon for Bingothon Winter 2023 is our 5th anniversary. And out of those 5 years, Fred Hutch has been our charity partner for 3 of them. So it's an amazing milestone that we're reaching here. And so, with that said, hello, Guppy, once again.
Hey, Pika, hey, Flo.
Would you like to introduce yourself and talk a bit about Fred Hutch for those that are not familiar?
Absolutely, thank you. So, hey, everybody. My real name is Amitabha Gupta. My pronouns are he, him, but everybody at Fred Hutch and beyond knows me as Guppy. I work at Fred Hutchinson Cancer Center, which is a comprehensive cancer center out in the Pacific Northwest. So comprehensive cancer center means we have bench research, we have patient care, and everything in between. And so what Fred Hutch is really good at is having that pipeline that goes from the bench to the bedside and to the community and beyond. And so we're very fortunate to be here. We're in Seattle, in the heart of the tech capital. And so we're bringing in really good tech and research together, impacting patient lives and making it better for more people everywhere. And we are ever so grateful to have partners like you from all around the world for 3 years. I mean, we're really grateful to Bingothon and all the supporters.
All right, thank you. So, Flo, I see there's something you want to go ahead with.
Yeah. So let's get into like the actual question section in here while we're here. So we're doing these interviews basically on an annual basis. So what do you think are like the most interesting milestones that happened at Fred Hutch in the past year?
Yeah, so that's a great question. And it's been a really interesting and fun year. So I think when we last came on, I briefly talked about how Fred Hutch had merged with the Seattle Cancer. We used to be Fred Hutchinson Cancer Research Center. We merged with the Seattle Cancer Care Alliance to form Fred Hutchinson Cancer Center. And that has enabled us to be even more efficient at expediting the research that we do in the labs and in the bench and taking it to the clinic. So that has been an absolute step forward. And so a couple of the really big advances in the last year or so, we've developed new technologies that will make it much easier to diagnose whether somebody has, for men with prostate cancer, to be able to figure out their type of prostate cancer just based on a blood test. And that's absolutely incredible because that means that those patients who have prostate cancer and are being monitored, you don't have to go in and have a biopsy every few months, every few years, which is really painful and could leave a scar. Instead, you just take it from the blood, and that way our patients are not feeling as much trouble. We've also improved our screening and detection with breast cancer. We've developed a few new detection agents so that we can detect not only who has breast cancer, but what type of breast cancer they have, so we can match the patient's disease with their treatment. And that's really the goal, is being able to absolutely match each unique patient with the right treatment at the right time and in the right dosing so that they have the best outcome against the cancer without the effect on quality of life.
So that's interesting. So basically, that new technology. Is there any more details you can talk about?
Do you want to talk about the breast cancer one with the imaging?
Yeah.
Yeah. So what's really cool is that as part of this merger, we've also built a new imaging suite, and we've got some state-of-the-art imaging equipment that allows us to look more deeply at people's solid tumors and find where they are in the body. And we're sort of marrying that with technology that basically can detect. So we're creating molecules, either small molecules or antibodies, that will bind to certain proteins on the surface of a cancer cell. And those have something that will light up so that we can see it on this screening technology that we have. And so we're developing more of those really targeted molecules or antibodies that can find very specific markers on the protein of the surface of cancer cells. So then we can say, oh, the surface of this cancer has this, that is the makeup of this cancer, and now we can treat it with this. And so it's opening up this field of something called theranostics. So creating the same thing that can be a diagnostic and a therapy. So you find it, so let's say you find an antibody so those are the Y-shaped molecules that your body normally makes. You can find one that will recognize abnormal proteins and molecules on the surface of cancer cells. And so you take it and you put a really low dose of radiation on it, and it'll go bind, and you can see it under imaging. And if you can see it under imaging, then you can put something heavier, like something more destructive on it, and it'll go to the same spot because you already know you have a target.
Nice. And it's nice to see that like part of this is also like thanks to that merger that you talked about, and how this is allowing to overcome like certain challenges and things like that. And on the subject of challenges, do you still have particular challenges at the moment that is currently being faced in terms of research at the moment?
So I think let's divide this into three sections, right? Like I'll start with the research side. So on the research side, like, one of the hardest things is the fact that a lot of our research traditionally has not involved including everybody. Like it is a very small percentage of the population that has been part of studies and trials. So what we know about the makeup of disease comes from a very limited pool of people. So a lot of the treatments and understanding of disease is not applicable to everybody across the world. And so we are making strides in trying to build relationships, build partnerships with other groups and people, reaching out, understanding what their lived experiences are with regards to medicine and the medical industry, if you will, and bringing them on and trying to find ways to intervene with screening or early detection in a way that is true to their beliefs and their systems. So we're not trying to go in and tell them what's right and wrong. We want to work with them and understand. So that's one part, is building that community, get more research. The other part that's really a little bit tricky is that fundamental research that just tries to understand the broad base of everything, is not getting as much funding as like research that is applicable at the clinic. And I get it, right? Like there are people suffering today. We want to be able to make treatments for them now. But the fundamental research will solve the problems that we don't even know we have yet, right? It's being the most prepared. We came together because of COVID, right? And during COVID, what allowed us to get out of that was fundamental research into how to design vaccines, what type of vaccines will work, finding new technologies, finding ways to stabilize mRNA, finding ways to make a subsection of a coronavirus. Nobody wanted to fund that work. Like, to the point, the Nobel Prize winner this year, she was forced out of her university at UPenn because they didn't think that research would work, because it didn't have an immediate application. But that fundamental research can have an application that we don't know yet. So I think that's a little bit of a struggle. That fundamental research still needs a little bit of work. On the patient side, I think I'll say that a lot of our treatments are still not precise enough. We're still giving, standard of care therapy that will affect multiple cells in your body, not just the cancer cells. And that can lead to a lot of side effects and really reduce the quality of life for patients. Like, some of those drugs, have really bad side effects. How can we get better at really matching a patient with the right treatment so that their quality of life is better, so that they can go on and live a good life for the rest of their life.
Okay, that's interesting. And especially one particular aspect I'm thinking about is what you mentioned about the fundamental research.
Mhm.
Because I would guess, like from my uneducated guess from what you said, that like one of the reasons why that research might not be having the funding it needs is because there perhaps is a lack of like immediate need, if that makes sense.
Yeah.
So would that in particular make sense, or are there additionally on top of that other reasons why that particular side of research is not getting the funds it needs?
No, I think the hard part is that the question being asked of what is your direct impact now? What is your disease relevance now? And it's not exploration based. And there's two parts. And I've heard these amazing stories, including the current Fred Hutch, President Director Tom Lynch, of how a discovery at the clinic was matched with a discovery at the fundamental research level. So basically, for example, Dr. Tom Lynch, when he was in medicine and he was rounding, he saw a lot of patients with lung cancer that looked a certain way. And when they were able to sequence it, they found there was an alteration in one gene called EGFR. But fundamental researchers had done all this work to understand, what does EGFR do? How does it signal? What does it do? How can we block it? Let's develop drugs that will block it to understand what it does at the basic level. And so you had this discovery in the clinic of a patient having a modified EGFR, and you had this fundamental research that was already there to say, oh, yeah, you just add this drug and it will stop it. And then suddenly that's when magic happens, right? And the funny thing is that, the genome has been sequenced since 2001. We've had the whole genome. We still don't know what 3/4 of the genome does. We have no idea. 3/4 of the genes that make us human, we have zero idea what they do. Nobody's doing research into that. But they're often altered in cancer, but nobody's doing the work to figure out what, how, when. And we need that work, because imagine if we knew all that, how many more things we could treat.
That'd go far.
Because somebody actually published a really interesting study that even after the human genome, so they looked at all the genes that people were studying before we had the whole genome sequence, and all the genes we were studying after we had the genome sequence, and they were basically the same. Understanding the whole genome didn't drive people to study other new things quite as much, because of that need for immediate response.
Okay, that makes sense.
Yeah. So, coming back to that merger between Fred Hutch and the Seattle Cancer Care Alliance, how would you say that things are generally now in that regard? And how did the merger go? Did it go well, or were there some initial struggles that you had to overcome? I'm certain there were.
I mean, yeah, it's you bring two different bureaucracies together. It's hard. People have their own way of working. People have their own filing system, their own coding system, and also with regards to data, right? Like, one is a hospital with patient data that has to be protected. One is a research center which hasn't had to deal as much with patient protected data. How do you merge those two data streams together while protecting patient privacy? So there've been some rocky moments, but there have been some amazing new collaborations that I've been able to see. So one of our researchers, Dr. Andrew Cowan, who works in multiple myeloma, was able to, because of the merger, be introduced to a bench scientist, Dr. Taran Gujral, who has developed a technology that will allow him to do profiling of any tumor with a whole combination of drugs to identify the right precise drug combination, and possibly how those cells will respond. So basically, now Andrew can take patient samples from multiple myeloma, which is a really hard blood disorder to treat and has a really high rate of relapse, give some samples to Thuron, who can identify based on just 40 to like 200 drugs. He can use machine learning to identify over 1 million combinations of the right drug that will work on that specific tumor. And then he can study it and see how it will evolve and how it's likely to relapse. So think ahead and have those backup treatments as well. So that is some of the possibility, the ability to take something from the hospital, from a patient, right into the lab and then right back.
Nice. Now we're gonna dig a bit into some stuff we did talk about like last time in our last interview last year. So one topic we touched upon was regarding CAR-T immunotherapy and basically the fact that you'd love to see it get more funding. So first off, could you please do like just a quick summary of what that topic touches upon, and just in general see if there's been any updates regarding that, like in the past year?
Yeah, that's an excellent question. So Fred Hutch is very well known for the bone marrow transplant. So that was one of the first curative treatments for all blood cancers, where people with blood cancers had their bone marrow removed and somebody else's bone marrow went in, and that was able to cure the cancer. And when they dug in it a little bit deeper, they discovered there was one specific type of cell, the T cell, that was being repopulated that was able to go attack the cancer cell. So we already knew about the cancer-fighting potential of the T cell. So some of our researchers asked, well, what if we trained T cells to already see cancers that they can't see? And that's where adoptive T cell therapy came in. And there's two different flavors of it. One is you adjust it to be able to see tumors based on what their internal makeup is. And then another one is you adapt it to be able to attach to the surface of any tumor based on what's on the outside. And that's what CAR-T therapy is. You're sort of basically taking an antibody, those Y-shaped molecules that are normally made in our body and attack different proteins. You're sort of cutting a little bit of an antibody off, sticking it on top of a T cell, and effectively creating like a Frankenstein arm or like a hook with a Velcro, right? And it will Velcro on to the surface of a tumor cell and then destroy it. And so that is where some of the work is going. And we know we have researchers that are looking at the surface of different tumor cells to look for different molecules to then make these CAR-T cells. And we've had a lot of success with CAR-T cells in blood cancers, particularly leukemia, particularly lymphomas, and multiple myeloma as well. But the question is solid tumor. And solid tumor is a little bit trickier because solid tumors sort of are built into tissue and co-opt other parts of the body for its protection and can do really strange things in certain regards. Like there are some, like for certain lung cancers, you'll see that the solid tumor is surrounded by immune cells, even T cells. But between that T cell and the tumor is another layer of immune cells called neutrophils that are blocking out the disease-fighting T cells and preventing them from destroying it. So the solid tumor has done something to make that section inaccessible. Or in the case of other like pancreatic cancer, there's something about the region around the pancreatic cancer where they've created something that will suppress the immune system and shut down any T cell that comes in. So the T cell can come in rip-roaring to destroy it, but there's these molecules there that just shut it down. So the next stage is trying to understand what are those specific differences in the different solid tumors that we can arm the T cells to better infiltrate the tumor and last when it is in the tumor for a longer time to destroy the tumor completely.
And so how do you think things are in that regard getting to that next stage?
Yeah, so that, sorry. Yeah, I guess that was the question. Yeah, so we've had a lot of success with some prostate cancer. We have a new prostate cancer CAR-T trial coming out. And one of the things that we discovered was that the putting a CAR T is not sufficient. It needs something else to like keep it stimulated near the prostate cancer. So a second phase of engineering went in that would keep reinvigorating the T cell when it was attacking the tumor, so it wouldn't be able to be shut down quite as easily. There are others where we've done some work with also changing sort of the programming of the cells. So in the process of making CAR T cells, it's sort of, you have to grow them, you have to edit them, and you have to grow them again. And sometimes they're a little bit older in their genetic programming. How do we deprogram that so that they feel that they are younger and so they can fight for a longer amount of time? So we're making some of those changes with some other CAR Ts as well to make sure that they are able to avoid being silenced by the immune system completely. And in other cases, we're also trying to think of how do we add secondary molecules. So there's a couple of different classes. You can there's two ways that the immune system can shut down the T cell. It can either grab onto something called like PD1 or PDL1, and that would put the T cell to sleep, or it would create a system where the T cell sort of just like sputters to a halt. So one is a brake and one is like preventing the accelerator from being hit. So we have to figure out for which CAR Ts do you need to add an extra therapy that will take the foot off the brake, and which one do you add an extra drug that will like press down on the accelerator to go destroy the tumor.
Yeah, that part must be the tricky bit.
Yeah, and it's different for different tumors. And so really understanding what does that make up? And that's where some of the fundamental research comes. How do we recreate those models of those tumors in non-human cells to really understand what happens to an immune cell when it gets into the zone of a tumor? How is it being shut down? And what could we give it as an assist?
Yeah, it's interesting to see how, as you said, you kind of come back then to the fundamental research and how that can then have an impact on many things, that included.
Yeah.
Because as you said, it can just kind of lead to, like, it's an exploration of many things, and you can from there you can just discover many things that can then be useful for so many other things.
Yeah, exactly. But the other thing is that we've been able to harness really cutting edge like microscope technology to really look deeper at each tumor to understand what their makeup is. Like, is it that there's no T cells around, and that should indicate you have to retrain T cells to be able to see what the surface is, or are there T cells that are around the tumor but they've been suppressed in one way or the other, or is there something else that is blocking the path of the T cells that you have to put in another drug to clear those out first so that the T cells can go in? So that's really where the personalized precision medicine comes in.
We'll have more to talk about precision medicine later on, but because there was some stuff I wanted to ask about that. But first, Flo, I think there was some stuff you wanted to talk about.
Speaking of fundamental research, now during COVID, we've heard of this new fancy term, so to say, which is mRNA vaccines. We've seen them all over the news. Now, something that's new now, which is just recently, I stumbled upon it upon just watching the news. BioNTech has recently released a cancer vaccine, which even the German health minister has advertised basically as a breakthrough in cancer therapy. Can you maybe tell us a little bit more about that?
So I don't know about which specific cancer vaccine they're talking about in this case, but that technology has immense promise, right? Because all you are doing is you are creating. Let's take a step back. What does a vaccine do? The purpose of a vaccine is to train your immune system to be able to recognize something that it needs to be destroyed. You're basically creating a wanted poster for your immune system, if you will. And so there's two parts of that. One is being able to figure out the unique features of the tumor that are not present in any of your other cells in your body that you can use to create that wanted poster. Because you want really specific description or really specific pieces so that whatever vaccine you create doesn't have that side effect of attacking other parts of your body. Then once you do that, you have to figure out which small subsection of that virus, protein, cancer cell is accessible to the immune system, so outside on the surface. And then you have to create the vaccine that will be able to attack that and go to it. Or so you're basically looking at a tumor cell, finding the piece that's outside on the surface that's unique to it, taking the coding, so the mRNA version of it, and that way your body makes the protein version of the small thing and it trains your immune system to attack. So that technology absolutely is like the next phase of precision oncology, because you can go into every patient's tumor, figure out what's unique, and create that mRNA vaccine. And that is why people are so excited about it, because it's much easier to make than a traditional protein vaccine. Because with a protein vaccine, you almost have to build a protein in a different organism, get it approved, make sure that your human body won't reject it. Here, it has none of that. Your body is just making something for the cancer cell to destroy. So that's why the technology is so breakthrough.
All right, very interesting. Yeah, and I'm sure we're gonna see more of that within the coming years.
And I think the other piece of that, for that to be truly successful, is you have to have that infrastructure to do that genetic analysis, to dive into what makes that tumor unique, being able to dive into every patient's unique tumor to figure out what is unique. But that takes work. Not every place has that capability to do that genetic screening for every person's tumor. So that's one piece. And the other is you have to have regulations that will allow for these quote unquote N of 1 trials. So if you're creating personalized treatments, normally with a clinical trial for something, you have to have a control group who is not getting the treatment and a test group who's getting the treatment. But if you're personalizing it, what is your control? How do you test whether the treatment is working or not? So figuring out that section of it as well.
So something that we often talk about is how Fred Hutch supports a patient's family.
Mm-hmm.
And you also have a program called the Survivorship Program. Can you maybe tell us a bit more about that as well?
Yeah. So let's take the patient family support first, and then we'll take the survivorship side next. So a person doesn't go through cancer alone, right? Like when a person has cancer, it affects their loved ones, it affects their family, it affects the caregivers who are going to look after them. It's a lot of burden keeping up with all the appointments you have to go to, all the treatments you have to get. How do you get to your screening? How do you get to your infusions? All of those. So we have a patient navigator program that is there to help patients go through the system, figure out insurance, figure out actually even so much as transportation. Like for some people, they need somebody to drive them to a treatment and get that infusion and then drive them back after because they'll be so woozy. How do we make that more easy? So that's one side of it. And for people, actually, yeah, and one more thing, like for people who are traveling from out of state, where do they stay? Where do they get food? They can't live in a hotel. What do we do with that? So we have a patient house as well that is near to Fred Hutch, where we can get people over on a shuttle as well. On the other side, with the survivorship, one of the things that we do is that we follow patients after they've gone through treatment, because treatment is often not the end of the road. Some of the earliest treatments that people gave were very toxic to other parts of the body because they targeted rapidly growing cells in your body. So they took out the cancer, but they affected something else. And you want to be able to watch that over time to see if there are any side effects. There was a class of drugs called taxanes that were given for breast cancer that often resulted in heart problems for people many, many years down the line. So being able to do that study of what happens to patients after they've gone through care is absolutely critical, because if Fred Hutch achieves its goal and achieves what we want to do, we will have a lot of survivors. We need to figure out how to make things better for survivors going forward. That's what we want. We want to be able to have everybody be a survivor, but have that quality of life merge with being a survivor, not just a survivor.
It's interesting, and plus, I think on top of that, it also relates back to a topic that, I mean, you've discovered also today as well, and in previous interviews as well, about like the particular needs of like individuals that can vary, like depending on their community, where they come from, and other factors like that. Where I guess one of the things that the survivorship program probably, like one of the challenges they have to face is indeed also the question of, okay, how do we reach out to like within that survivor community, how do we help them the most depending on their circumstances? And so that's why it's an important thing for that to exist, because for all these reasons.
And beyond that, like we have people that are also studied the finances for survivors, because there is something called financial toxicity that happens for cancer patients. A large number of our cancer patients, because of the treatment, because of the cost, because of being unable to work, they take on a huge financial load. They often have liens on property, or have to get a second mortgage or something on their property to be able to survive. Just the impact of cancer is beyond just the impact on your body. There is that financial element as well. And so we are also working to find supports and ways to help people and figure out who is at risk of having financial toxicity, because some treatments go on for a long time, and some people will fall off that treatment because it becomes a choice between treatment and food, and they'll pick food every time. How do we ensure that they're able to stay on that treatment for the longest time?
Yeah, there's going to be a additional challenge as well, understandably. Is there anything else you want to add on to that, Flo?
No, I was just thinking about, because I had this exact conversation just this summer.
Yeah. Do you want to share more about that, Flo, if you don't mind?
It's I gotta make sure. It was at another speedrunning event, and it was a person who's also just been diagnosed with cancer, and we were talking about that cancer therapy can often be very expensive, and yeah, he didn't know yet at the time if the insurance would pay or not, and I mean, it was European, so insurance and everything is different here in Europe and all, but it was certainly something that we were kind of worried about, but it looks like it's all managed now. But yeah, it's certainly something that's very, very crucial as well, that patients can afford the therapy.
Absolutely, right. And so there's a couple of other pieces in that are also really there. The fact that cancer therapy is so expensive, some people are afraid to get screened because they don't want to know, because they know what that cost means to their family. And how do we convince people that actually screening is better? You want to be screened earlier. You want to catch it as early as possible, because then you have the best chance of outcome and the lowest cost to you, because you're not doing, cutting edge therapies or like follow up. The earlier we catch it, the better. And for a group as young as this, like, I feel the biggest message is advocate to yourselves and your family members about screening when it is age appropriate, and being very consistent with screening, because the best cancer is the one we catch before it even begins and take it out.
Yeah, that's true. And I guess, once you have that combination, like ideally you'd have a combination of both, like removing like that sort of fear, because I guess it can be understandable that people might have that mentality of, if I don't see it, like, it's kind of like denying, because they which when you're afraid, I guess something that can happen, as well as ease of access to screening as well. That's one of those things that's important as well.
And I think the other part is also that I feel more people should figure out what their genetic risk factors are, to be informed, to be able to know when to adjust their screening. Because for some people, you don't have to screen until like 45, 50 if you don't have any family history or any mutations that could predict that you might get a certain cancer. But if you do have that genetic mutation, then yeah, we can be proactive. We can screen you at a younger age and figure out whether you have cancer before. So you're not like, everybody is not the same when they should get screened. And so people knowing their genetic history is going to be an important part of the future as well, of trying to catch cancer earlier.
That's actually an interesting question. Like, how would one be aware then of that genetic mutation? I guess it's part of that is knowing your family history of of past cancer history within your family. But is there anything else on top of that can help know?
So I think absolutely past family history. Like if a lot of your family members have had the same type of cancer, it may make sense to talk to a genetic counselor and see whether you have that similar, if there is something in your family history that will make you more likely to have a certain type of cancer. Like I know that every male in my family has had heart disease. And so I've talked to my doctor. I've tried to figure out how to stay on top of my heart and how do I monitor that so that I don't have the same problems. But we only know a few genes that are correlated, like the famous ones are the BRCA1 and 2 genes, which are associated with breast cancer, but also prostate cancer. And so if you have family members who've had breast cancer, ovarian cancer, prostate cancer, it's important to go get genetically tested because certain cancers are very strongly genetically linked like that.
Okay, so in that case, so basically it's a kind of thing where if you suspect that there might be there might be a history, so it is possible to get a genetic test that can tell you, oh, maybe you should get screened for this and for that sort of thing. Okay.
Or just be mindful, right? Genetics is a piece of information. It doesn't mean that if you have a mutation, you will definitely get cancer. And there's some fundamental research that we are doing to try to figure out which alterations are more likely to become cancer and less likely. But it is a piece of the information that you need, and you can adjust accordingly.
Yeah, it's what I guess with these sort of things, there's no absolutes. It's just more likely or less likely.
Yeah.
And you just have to act based upon, if you have reason to believe that something is more likely to be present or less likely
exactly
to be present. All right. So on to another topic that, you've talked about it already here today, and it's also also something that has come up in the past. It's regarding precision medicine. Like you've mentioned, for example, precision oncology, for example. And so I think I read some headlines from a couple of months back that seem to imply that there's more and more progress in that regard.
Yeah.
So is there more you can talk about that?
Yeah, so absolutely, right? I think with the way data is now and the way how far genetic sequencing has come, when the human genome was first sequenced, it cost, I think, close to $1 billion, and it took 15 years. Now you can get a person's whole genome overnight for less than $1,000. It's come a long way. So we can start unlocking more about the genetic risk factors for different cancers. We've also gotten better at understanding how that genetics can be translated, so the genetics is basically like the biggest possible instruction manual you can find, but each cell in your body uses a small subset. So we've gotten better at figuring out which small subset is being used in each cell, and sort of then determining from that what are the drivers and what's the programming for different cancer cells, how they change their programming. And then beyond that, like at the end of the day, that gets turned into proteins, which are just like the action bits. And we've gotten better at figuring out what the proteins are. And so all of those pieces are making precision, like the future of precision oncology, just like much closer. We have so much more access to the ways that we can slice and dice data and really understand truly why a person's cancer is unique. And even beyond that, we're able to, one of our fundamental researchers who basically was just, all he'd ever cared about was how does the DNA in your cell get packaged and put into cells, right? So each of us has like trillions of cells in our body. Each of them has DNA that's like 6 meters long in these like minuscule cells. How does it get crunched up into that, something that small? That's all he cared about. He looked at it in worms and flies, in mice and in humans. But the way that the technologies that he developed to study that, he's now been able to develop to be able to like look at all the tumor slices that are present on slides from years and years and years ago. And by doing that, we're starting to like uncover the drivers of ever more tumors. So we're getting even more information of the different pieces that are leading to different cancers. And that way we can be better prepared and better understand the path that cancer takes, like what changes, like how does it go from here to here? And if you imagine it as a highway, how do we put up a blockade on that highway?
Nice. And yet another way that about fundamental research, like that keeps highlighting the need for that to get more funding and even more research into it, because this is like clearly it's touching a lot of things, and it's amazing to see really how much that's doing. It's really good.
And precision oncology also applies to some of the imaging that we talked about, sort of being able to know what's on the surface and dig it out. And actually, I would be remiss if I didn't tell one more story where we have some really talented like lung cancer researchers. So basically, when your body knows something's wrong, long before you know it's wrong or some symptoms are showing. And in that case, like when tumors start to form, your body creates these things called autoantibodies. So those Y-shaped antibodies that attack yourself, and that's sometimes leads to autoimmune disease, but your body's already figured out something's wrong and it's created a response that's attacking a version of yourself. And so they developed a platform to basically identify autoantibodies from your body and figure out which ones are predictive of lung cancer. So they found a subset and they said, well, if you have some proportion of these, it suggests that you have lung cancer. And now they're converting that into the theranostic, a diagnostic and a therapy. And so being able to leverage, and so basically what happens is in making the proteins, and something goes wrong in the cancer cell and the protein gets made in a slightly different way and your body recognizes that. And so it creates that autoantibody. So it's really specific to the tumor. So they're able to find those, really use the technology that your body's already using against the tumor.
And that's the way to get really very early as well, which is one of the really important bits as usual with this.
And for lung cancer, it's really, really hard to screen because you never, you either have to have full body imaging or something else. So this is a way to do it non-invasively as well, to figure out whether, without going in and taking a biopsy to look for it.
Good. All right. And so my next question also related to some topics we discussed in the past. This one is really related to some of Fred Hutch really well-known work, because one thing that was covered when we talked about the bone marrow transplant is the graft versus host disease. And so I remember that there were a couple of methods that researchers were tackling in order to just kind of counter that, if you will.
Mhm.
I think even one of them was involving like the microbiome. I think you mentioned, which I know is a topic you're passionate about. I know we talked about it a lot. And so, well, first off, like just do a quick reminder of what the graft versus host disease is for those that might not be aware, and also just talk about that progress in those methods in the past couple of years or so to tackle that. If that makes sense.
And so, I think this brings together a lot of different elements. This brings together Fred Hutch's bone marrow transplant. It brings together precision oncology. It brings together immunotherapy, and it brings together my love of the microbiome. Bugs for life, right? No, I'll say so. When people have these bone marrow transplants, a lot of times you're getting bone marrow from somebody who's unrelated to you, and each of the cells in your body has a whole bunch of flags on it that basically tells your immune system that, yeah, this is me versus this is not me. And so when you get those cells from somebody else as part of bone marrow transplant, sometimes your immune system is like, when that person's bone marrow develops and becomes an immune system, it's like, wait, I'm supposed to recognize this, not this, and can attack the person who got the transplant, can attack their own organs and body parts. And this often happens in rapidly growing areas like the gut and the mouth. So one of the ways that our understanding of immunology, we've tackled it, is by really identifying which subpopulation of the T cells are likely to attack them, lead to graft versus host disease. And we've been able to very specifically deplete those by putting some antibodies on like magnets and pulling away those specific subsets of T cells before we do the transplant. That way we reduce some of the risk. But the other is the microbiome. And the microbiome, again, as we are able to get more sequencing and more data, we're discovering how much we don't know about the microbiome and how much there is to know, and how involved it is in human disease. So the microbiome is every bacteria virus that lives on you and in you. And there's as many bacterial and viral cells as there are cells that are you. So we are half bacteria virus, I guess. I mean, maybe more than that. We're basically a collection of bacteria at the end of the day. And so what some of our researchers have discovered is that it is the microbiome in your gut before you get the transplant. So we're starting to figure out which collection of microbes before you get the transplant are good, in that they will not react with the new T cells to trigger that graft versus host disease, versus which collection of microbes is more likely to work with the immune system and trigger it to lead to graft versus host disease. So there's always that interplay, because if you think about it, we've lived with those bacteria and viruses, and our immune system has come to some sort of understanding with it because it's always up against it. But that's not the case with graft versus host disease. And so that's some of the work that we've done, and we've discovered some different combinations that are good, some that are bad, and possibly how that affects which immune cells that specifically affects. So how can we shut down that signaling of that immune cell that is likely to react in the cases where you have a bad microbiome to start with?
So what is it that makes then the difference between like a good combination and a bad one?
It's a good question. We're still figuring that out. And I think that's part of the unexplained thing. We don't have enough data on that. We know certain bacteria are good. We know certain bacteria are bad, but we don't know all the bacterial species yet, right? Like that's part of the problem on many different levels, and we can dive into issues of technology, issues of sequencing, like how we do sequencing makes it difficult to discover new species, but now that's evolving as well. We can talk about that at a different time, because I think that's a whole lesson unto itself, and I'll go to the whiteboard and start drawing stuff. Go back to my roots of being a teacher. But I think that's part of the problem, is we still don't have enough data. We have not done the work to get all the combinations of microbiome, all the combinations of immunotherapy, immune outcomes, and then start to match those two together.
It almost feels as though if there were more fundamental research into the microbiome, maybe there'd be potential stuff to discover there.
Yeah, I mean, to your point, right? Like, it's where fundamental meets patient care, and that's where Fred Hutch is so amazing. Because I'll tell you this great story about some of the work that one of our researchers here, working with head and neck doctors, so they were able to get tissues from the mouth of cancer patients and healthy patients of and apparently dental hygiene is a problem. Like, we're not all great at dental hygiene, and so everybody's mouth has like some amount of inflammation and some amount of immune cells. But they were able to get these patient samples and discover a whole new class of T cells that nobody had ever seen before and known what they were, that is very specific at shutting down the rest of your immune system. And they're these super suppressive T cells. And the potential is endless. Like, if you can figure out, oh wait, how do you end up at that state? How do we stop that super suppressive state? How does the microbiome result in creating those specific T cells? You can start getting at treatments for that. It's that fundamental study and that fundamental understanding of what is the microbiome in your mouth, what is the microbiome around, and how do those two things interact.
Nice. Flood, is there anything you want to add on top of that?
I would just go basically into our last, if you want to say, question. It's not really a question anymore, but it's just is there anything that you feel really passionate about that you just want to talk about now? Anything that's currently going on at Fred Hutch which we haven't spoken about yet?
Yeah. So one of the, coming back to a question you had about survivorship, one of the other big questions is something called metastasis, when a tumor leaves the primary site and goes elsewhere in the body. And for often it's not the primary cancer that kills somebody, it's the metastasis. So we've formed a new group called MetX, which is bringing together experts in immunology, solid tumor, blood cancer, breast cancer, microscope specialists, to really understand the mechanism by which cancer cells leave their original site, go somewhere else, avoid the immune system while they do that, and sometimes sleep for 5, 10, 20 years before coming back. And so this program, MetX, is going to really dive deeper into that science of metastasis to start being able to devise treatments for people when they're going through that first round of treatment, to also wake up the metastatic cells that may be hiding and destroy them at the same time, to take away that fear. You don't want people looking over their shoulder for even after treatment, but also being able to detect when metastases are present as well.
You look like you want to say something, Pika.
Oh, there's definitely it's really another topic, but I was curious to I don't want to interrupt that particular line of thought. If you have more you want to say about it, but there's something else also, about another topic I was curious to ask about.
I think I've said what I need to about the MetX program. We've had researchers who have really great expertise in identifying the factors that help cancer cells evade and sleep, and how do we wake them up and how do we target them. So I'm just really optimistic of taking that to all solid tumors. So yes, lead on to your question.
It's regarding your love, the the microbiome, once again, because something you said that intrigued me was regarding the idea that the more we're learning about the microbiome, the more we realize that there's so much that we don't know about it. And so obviously here we've been kind of talking about it in the context of the graft versus host disease, but is there any particular unknown aspect that you feel particularly driven toward, like within that unknown, that you really feel like, oh my god, that'd be really cool if we discover more about that specifically, if that makes sense?
Yeah, and there's this tying all those threads together, right? Like there's that you want to think about the microbiome, meeting graft versus host disease, meeting precision oncology, meeting metastasis, because there are some bacteria and viruses that do make it more likely for certain tumors to metastasize. So there's this bacteria called Fusobacterium nucleatum, which is an oral bacteria where bad oral hygiene leads to it going to the gut. It leads to oral cancers, but it also leads to gut cancers. And when it leads to the gut cancers, those colorectal cancers are more likely to leave and go somewhere else and metastasize all around the body. And when they do, they take the bacteria with them. And so there's so much to unpack. Like, does that bacteria cause the cancer? Does it protect a cancer once it comes up? How is it changing the programming? Does it enter the cell? Does it rearrange the genome of the cell, causing the programming to change? What is it doing that is also allowing that to be invisible to the immune system? There's all these levels as we discover with new bacteria and viruses. What is it doing and how is it interacting specifically? Because there's another bacteria called Helicobacter pylori, which is associated with stomach cancers. And much of the world's population has it, but it doesn't lead to cancer here in the US, but it leads to cancer in Southeast Asia, in East Asia and Southeast Asia. It is the number one cause of stomach cancer in East Asia. What are the differences between those two? Why is it the same bacteria not causing cancer here versus there? And there's just so much more to learn and unpack on each of these. So first we have to discover the bacteria, viruses, figure out how they're interacting with our cells, and at which step. Because if it's intimately needed for the cancer to develop, could we treat cancer with an antibiotic? Like, just thinking about that. Like, you give an antibiotic to treat cancer. That's it. Yeah. That's just mind-blowing in my opinion. But figuring out which cancers are those that you can treat like that versus which ones where you need to do something else and something else, because the bacteria is a passenger, not a driver.
It's fascinating to see just all those layers of questions that those create and the implications that it could bring if like those were to find an answer like for each of those questions. So who knows how long that will take, but
we're getting faster, right? Like once we've developed the technology to ask those questions, it's easier to ask it for different things, right? Like the first step is figuring out how to develop a way to answer the questions that you have to ask. And once you do it, you just pipeline one more, and just see what they do. The next hard one is, how do they work in communities? Like, it's not just like one bacteria, one virus. How do they work in combination with each other? What is the relationship between those that makes a complex community? That an individual bacteria may lead to this, but this combination will lead to something else.
Yeah, considering how many of them there are present within the microbiome, I guess it makes sense that you can't really just look at them like only on an individual level. I guess you do have to look at them on how they interact with each other. Nice. Is there anything you'd like to add, Flo?
Nope. I would maybe just before we wrap everything up in here, anything that you feel like you didn't get to say yet, Guppy, anything that you'd like to say for everyone watching, everyone donating?
Yeah. So I will start by saying, Pika and Flo, thank you. It's been so great to chat with you two for these 3 years. And I've said it to you privately, and I'll say it publicly here. Like, you guys have become friends to me, and you've become friends to Fred Hutch. Like, I talk to you more than I talk to some of my other friends. Don't tell my other friends that. But it's so great to see your passion and to see your drive and to see what you've built with this community. So I can't thank the two of you and the rest of the team at Bingothon enough. Like, we are so appreciative for you and your leadership and for the team. And to all the supporters that are part of Bingothon, we couldn't do this without you. You are an essential part of our community. Cancer is a difficult, complex disease. COVID was complex, difficult. It takes a village. It takes all of us. And you are part of our village. We're doing this together. And we are eternally grateful to you and everything that you're doing to help us.
Well, I can certainly say thanks to you as well for always taking your time, coming on, talk with us, talk about what's going on. It's really amazing to just hear all of this firsthand from you. It's absolutely amazing.
Thank you, Guppy.
Of course. I mean, the more good information we can get out into the world, and you guys, that's the other thing that you are doing that, is having that massive impact. There's so much misinformation in the world because in the absence of good information, misinformation spreads. And what you are doing is helping spread good information to people who need it. So again, not just with the research, but also in this changing of the community. I cannot overstate how much of an impact you two and the team at Bingothon have had.
Thank you. Yeah, I'm glad to hear that there is a positive impact in what we do, and I hope that anyone who might have been there for watching this interview, whether it be in its full format or within like the little short formats that will be viewed during the marathon itself, has enjoyed listening to what Guppy has had to say, because every single time we learn something new, and I'm sure there'll be even more stuff to learn later on.
Next time I'll come with a whiteboard and I'll start like drawing some images. We'll go deeper into the next generation of sequencing technology and why that's so cool.
Yes, illustrations along with it. Yes, let's go. So yeah, thank you so much, Guppy. And for me, for now, those are my last words. Floha, any last words?
I can just say what you said. It's it's just been absolutely amazing. Thank you everyone for watching, for taking your time to just listening to this. And yeah, it's absolutely amazing. We love raising money for Fred Hutch. We love talking to you for this awesome cause, and yeah.
Thank you guys. Thank you everybody.
All right.
Appreciate you.
See you all.
All right. See ya.